The year was 1845. Across the fields of Ireland, a stench rose that farmers couldn't explain. When they reached into the earth to pull potatoes for the evening meal, the tubers fell apart in their hands, brown, soft, liquefied. Within weeks, the smell of rot hung over entire counties. Within a year, over 1 million people would be dead. The potato wasn't just food in Ireland. It was survival itself. A single acre could feed a family of 6 for an entire year. An Irish laborer consumed 8 pounds of potatoes every day, roughly 80% of all calories. There was no backup plan, no secondary crop, no reserve, just potatoes, day after day, generation after generation. And when the fungus Phytophthora infestans arrived on damp winds from North America, that singular dependency became a death sentence. But the catastrophe wasn't just biological. It was economic. It was structural. It revealed something most people never considered. How potatoes actually left the ground mattered as much as how many grew in it. Because in 1845, harvesting potatoes meant one thing: backbreaking, hand cramping, finger bleeding, manual labor. Every single tuber had to be dug by hand. Every family member, from grandmother to child, spent weeks bent double with a spade or a fork, prying potatoes from cold, wet soil. The work destroyed hands. It destroyed backs. And it took so much time that when the blight hit and rotting potatoes had to be sorted from healthy ones, there simply weren't enough hours in the day or hands in the field to salvage what remained. Harvesting by hand wasn't just slow. It was a hard ceiling on survival. If a farmer could only dig what his family could physically extract in the narrow window before frost, then he could only plant what he could harvest. Production was capped by human endurance. Expansion was impossible. And when disaster struck, there was no mechanical speed, no industrial efficiency, no way to rescue a crop faster than 2 hands and a bent spine. This limitation wasn't unique to Ireland. Across Europe and the young United States, potato farmers faced the same brutal math. Labor determined everything. A family farm might employ a dozen workers during harvest season, all of them on their knees in the dirt. The cost wasn't just wages, it was time. A man working alone could dig perhaps a 1/4 acre per day, maybe half if the soil cooperated. An entire field? Weeks of unrelenting toil. Then, in the 1850s, something changed. Not in Ireland. Ireland was still reeling, its population cut nearly in half by death and immigration. But in a small village in Northern Ireland called Dogue, a man named John Hanson was watching his neighbors struggle through another harvest. Hanson wasn't a wealthy landowner. He wasn't an engineer. He was a farmer who understood one simple truth. If you could mechanize the digging, you could transform the entire economy of the potato. What Hanson invented in 1852 looked almost comically simple. 2 large iron wheels, a broad flat blade called a share that slid horizontally beneath the soil, and a vertical wheel fitted with metal forks, 12 of them arranged like spokes, that rotated perpendicular to the direction of travel. The machine was pulled by 1 or 2 horses. As it moved forward, the share lifted the entire ridge of soil and potatoes. Then the spinning wheel, powered by the forward motion through a system of gears connected to the wheels, struck the loosened earth crosswise and flung it, along with the potatoes, 3 to 4 feet to the side. The genius wasn't in lifting the potatoes. Plows could do that. The genius was in the separation. That spinning wheel, rotating at 90 degrees to the drill, scattered soil and tubers apart. Potatoes landed on top of the freshly turned ground, exposed and clean enough that gatherers could simply walk behind and pick them up. No more digging through compacted earth, no more sifting clods by hand. The machine did the hard part. Hanson secured his patent on July 30th, 1855. Within months, he was conducting trials on farms across Scotland and into Ireland. The results were undeniable. On November 15, 1855, a public demonstration took place at Athelstane Ford in Scotland. A crowd of local farmers gathered to watch Hanson's machine work. The Fifthshire Journal reported that the digger progressed steadily, digging one drill at a time and scattering thoroughly out the tubers. Few potatoes were injured, almost none were left buried. The machine was of very simple, although ingenious construction, and is worked easily by a pair of horses. Orders flooded in. By 1856, trials were being conducted across Scotland and into England. Farmers who'd spent lifetimes bent over potato rows suddenly had an alternative. But the machine wasn't without problems. The spinning action required significant draft power. Pulling the digger through heavy or wet soil demanded strong horses and constant attention. If the share was set too deep, it brought up too much earth, burying potatoes under clods. If set too shallow, it missed tubers entirely. Achieving consistent depth on uneven ground became an art. Still, the transformation was undeniable. A farmer using Hanson's spinner could dig up to 3 acres per day. That was 10 times what a man could manage by hand. 12 workers following behind could gather what had once required 50. The economic implications rippled outward immediately. Larger farms became viable. Marginal land could be brought into production. Farmers who'd been limited by labor shortages could finally expand. But Hanson's spinner was just the beginning. Across the Atlantic, another man was watching his own neighbors struggle with the same problem, and his solution would take the concept even further.
Isaac Wolverton Hoover was born in 1845 in Ohio's Erie County, into a world where farming meant gambling everything on weather, soil, and muscle. His father returned from the California gold rush empty-handed and settled the family on 115 acres of stubborn Ohio dirt. Isaac grew up working that land, learning stonemasonry from his father, understanding that farming at scale required more than hope. It required systems. By 1875, he had established his own operation near Avery, Ohio, and focused his energy on potatoes. The crop made economic sense. Ohio's soil suited them, markets were expanding, but the same problem that plagued farmers everywhere constrained him: harvest capacity. Isaac could plant 10 acres easily enough. Digging them out was another matter entirely. He'd heard about mechanical diggers. Simple plow-type lifters had existed since the 1860s, and Hanson's spinner had made its way across the Atlantic. But none of them quite solved the problem Isaac saw. Spinners scattered potatoes too far. Simple plows left them buried in clods. What was needed was something that could lift tubers, separate them from soil, remove weeds and vines, and deliver clean potatoes in a concentrated area for easy gathering. In 1884, Isaac went to work. He wasn't an engineer by training, but he understood mechanical principles and possessed what his contemporaries called an inventive mind. His prototype combined several innovations into one machine. Like Hanson's spinner, it used horses for power and forward motion, but instead of a spinning wheel, Isaac designed an elevator, a continuous chain of steel bars linked together with gaps between them. Here's how it worked. A broad, curved share blade mounted at the front of the machine slid under the potato row as the digger advanced, lifted by ground contact and angled to scoop up the entire ridge. Soil, potatoes, vines, debris all rose together onto the elevator. As the material moved upward on the chain web, soil and small stones fell through the gaps between the bars. Larger stones typically slid off the sides. Vines and stalks were carried to one side and discharged separately. The potatoes themselves, too large to fall through but small enough not to be crushed, traveled the length of the elevator and were deposited in a neat row at the rear of the machine or directly into a trailing wagon. The elevator was powered by the digger's wheels. Large, cleated iron wheels on both sides of the machine rotated as horses pulled it forward. Through a system of gears and drive chains, this ground-driven motion transferred power to the elevator mechanism, keeping the steel bar chain in constant motion. An operator sat on a seat mounted above the axle, controlling depth and monitoring the machinery. The separation was far more effective than spinning. Potatoes emerged relatively clean and undamaged. The concentrated delivery meant gatherers didn't have to search across a wide scatter pattern. They simply followed the machine and picked up what it left behind. And crucially, the digger could be adjusted for different soil conditions. Depth wheels controlled how deep the share penetrated. Different elevator speeds accommodated wet or dry ground. Isaac filed his patent application in March 1885. Patent number 318254 was granted May 19, 1885. According to the application, the machine had mechanisms for digging or removing the tubers from the ground, sifting and separating them from the earth, stones, weeds, and stalks, and delivering them at the rear of the machine, on one side into a receptacle or upon the ground to be gathered up, and the weeds are then discharged from the machine on the opposite side from the delivery of the potatoes. That first winter, Isaac built 10 more diggers in his barn. Word spread among his friends and neighbors in Erie County. The machines worked. A farmer using a Hoover digger can harvest up to 500 bushels per day. That's 40 times what he could dig by hand, maybe more in good soil. The economic transformation was immediate. Labor costs plummeted. Harvest windows widened. Farms that had been marginal suddenly became profitable. In 1886, Isaac partnered with his brother-in-law, Albert Prout, and they formed Hoover and Prout Company to manufacture the diggers commercially. They started small, 50 machines that first year, but demand exploded. By the 1990s, they were shipping hundreds of diggers annually. The company grew rapidly, driven partly by strategic marketing. In 1893, the Hoover digger was featured at the Chicago World's Fair, where it won widespread acclaim. Later, at the Trans-Mississippi Exposition, it received a gold medal. The timing mattered. The 1990s saw explosive growth in American agriculture. Railroads connected farms to distant markets. Canning and preservation technologies created year-round demand, and mechanization was transforming every aspect of farming. McCormick's reaper for grain, steam-powered threshers, steel plows. The Hoover digger fit perfectly into this wave of innovation. By 1916, the Hoover Manufacturing Company, no longer Hoover and Prout, was producing 5,000 machines per year and shipping them worldwide. The factory employed nearly 100 people. They'd expanded the product line to include potato planters, sorters, sprouters, and harrows. Farmers could now purchase an integrated system for the entire potato production cycle. But the design kept evolving. Early diggers were entirely ground-driven, which meant their operation depended on traction and forward speed. If the horses slowed, the elevator slowed. If they stopped, everything stopped. By 1913, Hoover responded to the arrival of tractors by offering diggers with gasoline engines mounted directly on the machine. These auxiliary engines powered the elevator independently, removing the load from the horses, which now only had to pull the digger forward. Optional attachments proliferated. Different elevator sizes accommodated different soil types. Open rattle chain elevators worked better in sticky clay. Rolling coulters, disc blades mounted ahead of the share, proved particularly popular for sweet potato harvesting, cutting through vines and surface vegetation before the share entered the ground. Road tires replaced field wheels for easier transport between farms, and picking attachment allowed wooden crates to be mounted on the side of the digger so potatoes could be loaded directly into containers rather than dropped on the ground. The Hoover was not the only elevator digger on the market by the early 1900s. Competitors emerged, each with variations on the theme, but the Hoover earned a reputation for reliability and solid construction. Farmers trusted it. It didn't break easily. Parts were available, and crucially, the company supported its products. In 1926, after 40 years of production, Isaac Hoover sold the company to John Deere Plow Company. He was 81 years old. Deere moved production to Syracuse, New York, and for a time marketed the machine as the John Deere Hoover potato digger, acknowledging the name's value. The Hoover family continued to own and operate the original Ohio factory for other ventures. Isaac Hoover died on March 4, 1941, at the age of 96. In his lifetime, he'd seen the potato harvest transform from a hand labor bottleneck into a mechanized process that could keep pace with industrial-scale farming. His digger had lightened the burden of crop harvesting and decreased the cost of producing one of the most common articles of food in America. But even as the Hoover digger reached its peak production, the next revolution was already taking shape, because the elevator digger, for all its advantages, still required hand labor to gather the potatoes. The machine only did half the job, and in the mid-20th century, engineers began asking, what if the machine could do it all?
The ground-driven potato digger, whether spinner or elevator style, held its dominance for nearly 70 years. Through two world wars, the Great Depression, and massive agricultural transformation, farmers relied on machines pulled by horses, then tractors, powered by wheels turning against the earth. But by the late 1940s, three forces were converging that would render these machines obsolete: labor shortages, tractor technology, and the brutal economics of post-war farming. Labor was the critical factor. During World War II, millions of farm workers left fields for factories or military service. After the war, they didn't come back. Industrial wages outpaced agricultural pay. Young people moved to cities. And crucially, in regions like Scotland and England, school authorities began restricting or eliminating the practice of releasing children from classes for harvest work. By 1962, that source of seasonal labor was gone entirely. Farmers who'd relied on 20 gatherers following their diggers suddenly couldn't find 5. Simultaneously, tractors were becoming universal. By 1950, horse-powered farming was rapidly disappearing from commercial operations. Tractors offered more than just pulling power. They provided the power takeoff, or PTO, a rotating shaft driven by the tractor's engine that could power implements independent of ground speed. This seemingly simple innovation unlocked enormous possibilities. Early adopters quickly realized the advantage. A spinner driven by the PTO could maintain consistent digging speed regardless of how fast the tractor moved. Operators could slow down in difficult soil without losing elevator function. They could increase spinning speed to throw potatoes farther in dry conditions or reduce it in wet soil to minimize damage. The decoupling of forward motion from mechanical operation transformed flexibility and efficiency. But the real revolution came from a different direction: the elevator digger. In the 1930s, American designs had been introduced to Britain. These machines featured improvements over the Hoover design: better separation, gentler handling, more precise potato delivery. By the early 1950s, manufacturers like Ransom's and Johnson's in England were producing elevator diggers that mounted directly to tractor 3-point linkage and ran entirely from the PTO. The advantages were immediate. Tractor-mounted diggers eliminated ground-driven mechanisms entirely. No more cleated wheels, no more chains connecting wheel rotation to elevator motion. The PTO powered everything directly, making the machines lighter, more reliable, and easier to maintain. Depth control became a matter of adjusting the tractor's hydraulic lift rather than fiddling with depth wheels. And the machines could operate in conditions that would bog down ground-driven equipment: wet clay, recently irrigated fields, uneven terrain. But even these improved diggers still required hand gathering. Potatoes came out of the ground cleaner and in neater rows than ever before, but someone still had to walk behind and pick them up. That limitation drove the next innovation: the complete harvester. The idea was straightforward. Why stop at digging and separating? Why not build a machine that lifted potatoes, cleaned them, and loaded them directly into bags or trailing wagons? By the early 1950s, several British companies were attempting exactly that. Names like Byfleet Machine and Tool, Globe Harvester, Johnson Engineering, Root Harvesters, and Minns Manufacturing all introduced complete harvesters between 1950 and 1955. These machines were more complex by an order of magnitude. They still used the basic elevator principle: a share blade lifted the potato row, and material moved upward over chains or webs while soil fell through. But after the initial lift, potatoes encountered multiple separation stages. Secondary elevators used rubber-fingered hedgehog rollers to remove clods. Blower systems directed air across the moving crop to carry away light debris and vine material. Electronic sensors, primitive by modern standards but revolutionary at the time, could distinguish between potatoes and stones based on weight or density. Mechanical fingers, guided by pneumatic systems, could pluck out anomalies as they passed. After cleaning, potatoes moved onto a picking table where workers stood on a platform mounted on the machine itself. These workers removed any remaining stones, damaged tubers, or debris by hand as potatoes moved past. The clean crop then traveled onto a side elevator and into a trailing wagon, or was loaded into sacks mounted on a harvester. The entire process happened continuously as the machine advanced. The first of these complete harvesters had teething problems. They were heavy, requiring powerful tractors. They were expensive, costing many times what a simple digger cost. Mechanical complexity meant frequent breakdowns. And crucially, they required skilled operators who understood the intricacies of multiple systems working simultaneously. Adjustment was an art. Elevator speeds had to be matched. Separation web tension needed constant monitoring. Too fast and potatoes were damaged. Too slow and soil accumulated, clogging the machinery. By 1952, if you were a Scottish farmer looking to purchase a complete harvester, you had choices, but all the manufacturers were English. Scottish farmers watched demonstrations with interest but hesitated to invest. The machines could harvest between 2 and 4 acres per day. Impressive, but not enough to justify the cost for smaller operations. And the hand-picking element remained. Workers still rode the machines, standing for hours removing debris. The complete harvester reduced labor requirements but didn't eliminate them. Then, in the late 1950s, a German company called Germa entered the market with a machine that would change everything, the VP, marketed in Britain as the Universal. The Germa Universal appeared in 1963, imported by Richard Pearson near Boston, Lincolnshire. This machine refined every aspect of the complete harvester design. Continental-style webs replaced traditional chain elevators. These webs used rubber or synthetic materials that were gentler on potatoes and more effective at separating soil. The rubber-fingered hedgehog separator became standard, replacing manual clod removal for most of the cleaning process. Most significantly, the Universal offered multiple output options: a bagging platform for loading into sacks, a bunker for temporary storage, or an elevator for continuous unloading into trailing wagons. The bunker option proved transformative. Earlier harvesters required a tractor and wagon running constantly beside them, matching speed and position while potatoes loaded continuously. This was difficult, inefficient, and required precise coordination. The bunker system allowed operators to fill the onboard hopper, typically holding several hundred pounds, then signal for a wagon, empty the bunker in seconds, and continue harvesting without stopping. By 1967,
The economics of potato harvesting in the 20th century tell a story of relentless cost pressure meeting mechanical innovation. Every advance in technology answered a specific financial pain point, and every pain point emerged from the same source: labor. In the early 1800s, before any mechanization, labor costs dominated potato production. Records from Ireland before the famine indicate that harvesting occupied 20 to 30 worker days per acre. A typical cottier family, landless laborers renting tiny plots, survived on what they could grow and harvest themselves. When they worked for wages, they earned perhaps a shilling per day during harvest season. The math was brutal. Harvesting an acre of potatoes cost more than the crop was worth unless you owned the land and did the work yourself. This economic trap limited scale. You couldn't expand beyond what family labor could handle unless you could afford to hire help. But hired help meant paying cash wages in an economy where most farmers operated on barter and subsistence. The result was stagnation. Farms stayed small, production stayed limited, innovation was impossible because there was no capital to invest. The arrival of Hanson's spinner in the 1850s fractured this equation. Suddenly, the labor requirement dropped by 90%. An acre that had required 30 worker days now needed 3. The capital cost of the machine, typically between 20 and 30 pounds in the 1860s, could be recovered in a single season if you harvested more than 5 acres. For farmers on marginal land, this was transformational. For the first time, expansion made economic sense. But there was a catch. You needed horses, and horses weren't cheap. A working draft horse cost 15 to 20 pounds. You needed at least 2 for a spinner, sometimes 3 in heavy soil, plus feed, harness, maintenance, and the labor to handle them. The machine itself might be affordable, but the total system required significant capital investment. Small cottiers and landless laborers, the very people who most needed mechanization, couldn't afford the entry cost. This created a bifurcation in farming. Larger farms that could afford horses and machines expanded rapidly. Smaller operations, unable to compete, either consolidated or failed. The social consequences rippled through rural communities. The cottier class, already struggling, found themselves increasingly unemployed as machines replaced hand labor. Many emigrated. Others moved to cities seeking factory work. The rural population declined even as total agricultural production increased. By the 1880s, when Hoover's elevator digger appeared, similar dynamics played out in America. The digger cost between $75 and $150, depending on options, roughly 3 months' wages for a farm laborer. But it could replace 20 workers during harvest. The payback period for a commercial potato farmer was measured in weeks, not years. The Hoover Manufacturing Company sold thousands of machines, not because farmers loved technology, but because the alternative, hiring enough labor, was becoming impossible. Labor shortages drove adoption more than any other factor. During World War I, with young men overseas and factories offering higher wages, farms struggled to find workers. Mechanization wasn't optional, it was survival. By 1920, any serious potato farmer operated a digger. The hand-dug potato farm had become an anachronism. The Great Depression briefly reversed this trend. With unemployment soaring, labor became cheap again. Some farms actually sold their diggers and returned to hand harvesting because workers would accept wages below the cost of operating machinery. But this was temporary. By the late 1930s, as the economy recovered and war approached, the labor market tightened again. Mechanization resumed. World War II accelerated everything. With agricultural production designated a national priority and millions of workers in uniform, farms faced unprecedented pressure to increase output with fewer hands. The government subsidized equipment purchases, manufacturers ramped up production, and crucially, tractor production shifted from steel-wheeled monsters to rubber-tired machines with hydraulics and PTO systems that could power implements far more efficiently than ground-driven designs. The post-war period saw the final evolution, the complete harvester. These machines cost between $3,000 and $5,000 in the 1950s, roughly $35,000 to $60,000 in modern dollars. But they could harvest 8 to 10 acres per day with a crew of 6 workers instead of 30. For large commercial operations, the economics were overwhelming. A 100-acre potato farm could recover the machine cost in 2 seasons. A 500-acre operation paid it off in 1. But complete harvesters created new problems. They were complex, requiring specialized maintenance. They were heavy, compacting soil and requiring larger tractors. They were delicate in ways that simple diggers weren't. Electronic components failed in dusty fields. Hydraulic seals leaked. Bearings wore out under constant vibration. Downtime during harvest season was catastrophic. A broken harvester meant watching crop value evaporate while waiting for parts or repairs. This drove a new industry, agricultural contracting. Farmers who couldn't justify owning a harvester hired contractors who owned multiple machines and traveled from farm to farm. This spread the capital cost across many clients, but created scheduling challenges. You harvested when the contractor arrived, not when conditions were optimal. If weather turned bad or the machine broke down at someone else's farm, your potatoes might sit in the ground for extra weeks, risking damage or quality loss. By the 1970s, potato harvesting had effectively split into 2 worlds. Large commercial operations, farms exceeding 500 acres, owned their equipment, employed specialized mechanics, and operated with industrial efficiency. Small farms either hired contractors, bought used equipment, or exited potato production entirely. The middle ground collapsed. You scaled up or you got out. The 1980s brought the final transformation: self-propelled harvesters. Instead of being pulled by a tractor, these machines had their own engines, transmissions, and drive systems. They looked more like combines than implements, massive, specialized vehicles built for one purpose. Self-propelled harvesters offered several advantages. They were more maneuverable, with 4-wheel steering that allowed tight turns at field edges. They were faster, traveling at speeds that would destroy a trailed machine. They were more stable, with suspension systems that kept separation webs operating smoothly over rough ground. But they cost $200,000 to $300,000, sometimes more. No small farmer could justify that investment. Even many large operations hesitated. The machines only made economic sense if you harvested thousands of acres or operated a contracting business serving multiple farms. This resulted in further consolidation. By the 1990s, potato farming in developed countries had become an industrial operation, dominated by large corporate farms and specialized contractors. Yet in developing regions, the old machines persisted. In parts of Eastern Europe, South America, and Asia, ground-driven spinners and simple elevator diggers remained common through the 1990s and into the 21st century. Not because farmers preferred them, but because they were affordable. A used spinner could be purchased for a few $100s and pulled by a small tractor or even horses. Repairs could be done by any blacksmith. Parts could be fabricated locally. This created a technological time capsule effect. Visit a small farm in rural Romania or Peru, and you might see a Hansen-style spinner built in the 1960s still operating. The design hadn't changed meaningfully in over a century, because it didn't need to. For farms under 20 acres, the economics of simple mechanization still worked. Modern precision agriculture has introduced yet another layer: GPS-guided harvesting.
But underneath all this technology, the fundamental mechanical principles haven't changed since Isaac Hoover's 1885 patent. A blade lifts the row, material moves across a web or chain, soil falls through. Potatoes are separated and delivered. Everything else, from PTO power to computer vision, is refinement, not revolution. Stand in a modern potato field during harvest, and you'll witness a machine that would astonish John Hansen and Isaac Hoover. Yet they'd recognize its fundamental operation immediately. That tension between radical transformation and underlying continuity defines the history of agricultural mechanization. The story of the potato digger isn't just about machines. It's about the relationship between technology, labor, and economics. Every innovation emerged from a specific problem, usually involving the cost and availability of human workers. Hansen's spinner solved the backbreaking labor bottleneck of manual digging. Hoover's elevator addressed the soil separation challenge. PTO-driven implements eliminated ground speed limitations. Complete harvesters integrated digging, cleaning, and loading into one operation. Each step reduced labor requirements and increased output, but each step also required more capital and more specialized knowledge. This created winners and losers. Large farms with access to capital could invest in machinery, expand operations, and drive down per-unit production costs. Small farms without capital couldn't compete and either consolidated or exited. The pattern repeated with every technological advance. The result, over 170 years, was the near total industrialization of potato production in developed countries and the concentration of farming into fewer, larger operations. But the human cost deserves acknowledgement. The workers who once followed diggers through fields, the seasonal laborers, the school children released from classes, the coddiers and smallholders, didn't simply disappear when machines replaced them. They moved to cities, often into factory jobs that were equally difficult but offered better wages. Their communities changed. Rural populations declined. Traditional farming knowledge was lost as mechanization made it obsolete. Yet, mechanization also delivered undeniable benefits. Food became cheaper and more abundant. The backbreaking physical labor that destroyed bodies and limited lifespans was eliminated. Productivity increased exponentially. A modern self-propelled harvester with 3 operators can harvest potatoes in 1 day than 200 workers could dig by hand. That efficiency feeds populations that would otherwise face scarcity. The technological lineage is remarkably direct. Hansen's spinner demonstrated that mechanical separation was possible. His rotating wheel throwing soil and potatoes perpendicular to the direction of travel established the principle that would dominate for decades. Hoover's elevator refined that concept by using continuous motion instead of impact force, reducing damage and concentrating delivery. Mid-century complete harvesters added cleaning and loading stages, but retained the elevator principle. Modern automated machines layer sensor technology and computing onto the same fundamental mechanical operation: lift, separate, deliver. What's changed isn't the core concept, but the precision and integration. Contemporary harvesters adjust digging depth in real time based on GPS-mapped soil data. They vary web speed and separation intensity automatically as soil conditions change. They use computer vision to identify and remove defects that human sorters would miss. They log yield data for every section of field, creating maps that inform next season planting decisions.
This precision matters economically. A harvester that damages 5% of crop instead of 3% costs the farmer thousands of dollars in a single field. One that leaves 2% of potatoes buried instead of 1% represents tons of lost revenue. The mechanical refinements that reduce these losses, gentler webs, more sophisticated separation, better depth control, justify their cost many times over for commercial operations. Yet, in other parts of the world, simpler technology persists because it fits different economic realities. A small farmer in the Andes or Eastern Europe doesn't need GPS guidance or optical sorting. They need affordable, reliable digging that reduces labor enough to make potato farming viable at 5 or 10 acres. A used ground-driven spinner or simple elevator digger purchased for a fraction of what a modern harvester costs serves that purpose perfectly. This technological stratification will likely continue. As automation advances, large commercial operations will adopt increasingly sophisticated systems, perhaps autonomous harvesters that require no operators at all, guided by AI that optimizes every aspect of the process. But smallholder farmers will continue using machines whose designs trace back decades or even centuries because those machines work and they're economically accessible. The potato digger's history also illuminates broader patterns in agricultural mechanization. Almost every major farm implement follows a similar trajectory: hand labor, animal-powered mechanization, engine-powered implementation, integration of multiple operations, automation, and precision agriculture. The timeline varies by crop and region, but the pattern recurs. What's striking is how long each stage persists. Hanson's spinner design remained essentially unchanged for 70 years. Hoover-style elevator diggers dominated for half a century. Even today, machines whose basic architecture was established in the 1960s remain in production. Agriculture is conservative. Farmers invest in proven technology, not experimental designs. Only when economic pressure becomes overwhelming does wholesale adoption of new methods occur. Looking forward, the next transformation might not be mechanical, but biological. Precision breeding and genetic modification could produce potato varieties bred specifically for mechanical harvesting. Uniform size, identical maturation timing, skins resistant to mechanical damage. Some research even explores potatoes that naturally separate from soil, reducing separation requirements. If successful, these developments would shift innovation from machine to plant, fundamentally altering what harvesting equipment needs to do. But that future remains speculative. What's certain is that the principles established by Hanson, Hoover, and their contemporaries will continue to underpin potato harvesting for the foreseeable future. The share blade lifting the row, the moving web separating soil from crop, the continuous motion that processes material faster than human hands ever could. These concepts, refined over 170 years of incremental improvement, represent the mechanical knowledge that transformed potatoes from subsistence crop to global commodity. In the end, the potato digger's history is about problem solving. Farmers faced a constraint, harvesting capacity, that limited everything else. Engineers and inventors, often farmers themselves, developed machines that removed that constraint. The machines weren't perfect. They created new problems even as they solved old ones. But each generation of innovation moved the needle, expanding what was possible, reducing what was required, transforming what had been impossible labor into mechanical routine.
That's the legacy worth remembering. Not just the machines themselves, but the human ingenuity they represent. The willingness to experiment, to fail, to iterate, and ultimately to succeed in making the impossible merely difficult, and the difficult merely standard.